This summer, I've stumbled upon a fascinating article, and I didn't understand it completely. Like, I didn't get anything, but I have managed to understand a small part of it. And that's what I will tell you in the beginning. And then I will apply it to the bundles of Banach algebras. Okay, so it will be a little weird because it's a part of a bigger picture, but I'll try to make it small. Let's begin with the definition. Suppose we have a Hilbert space E, and E is finite dimensional, which means it has, and also it has an orthonormal basis, E1, E2, etc., En. We will suppose we have suppose we have an ideal in a ring, which I will call, which I will denote by this symbol. I will explain what it is later in a second. This is a two-sided homogeneous am I right? I'm not sure. I have problems with spelling too. Ideal. And this ring is a ring of noncommutative polynomials. So I suppose we can look at it as a ring I suppose we can write that it's a ring which I'm sorry. No.
So
okay. Yeah. So I'll try to see it this way. So it's a vector space because it's an algebra. It's a C-vector space with the basis like this: Z1, X1, XE1, XEn. This is a basis. And EK belongs to the set 1, 2, etc. N. And so the multiplication on these non-commutative polynomials is very natural. So we can set the product of these basis vectors of this algebra equal to just the natural. So it's a very natural object. I think that I just don't know the right words to formulate.
In other words, this is the free algebra of finitely many generators. or equivalently, the tensor algebra of an n-dimensional vector space. Is that correct?
Yeah. That's completely true. Okay. I just forgot except the symmetrical algebras and anti-symmetrical algebras, there also exist tensor algebras. Okay, so that's a very natural thing. So we take an ideal in this very natural ring, and we will denote by I with a wave on it. I'm also wrong. I'm really sorry. I should prepare better. Just a second. I'll try to make it better. So I think that if I'll begin from the definitions, no one will understand me at all. So I'll begin with another definition. So we take this. Forget about this Hilbert space. I'm really sorry. So that doesn't matter. So sorry. So we take this ideal, and when we want to construct an algebra associated to this ideal, let us begin with the my most beloved definition, the full Fock space, which we'll denote by f of e. So that's a Hilbert space, and it's a Hilbert sum of Hilbert spaces which are E tensor of n, where E tensor k, which the sum by k, where E is the Hilbert space, the definition of which I have erased. Okay, so this is called full Fock space. So I said that there will be an algebra, a non-commutative disk algebra. So let's begin with its definition. So I will denote by Si an operator on the full Fock space from f of e to f of e, which will do the following. On the basis of vector of this Hilbert space of the form E1, EI1 tensor, etc., tensor EIM, it will just multiply to it EI to the left. So that's a rather natural thing, a rather natural operator. So now let's call AN the Banach algebra generated by these operators. These are also called creation operators.
So when you say generated, you mean that this is subalgebra, the subalgebra in the algebra of all bounded operators on E.
Yeah, exactly.
More or less subalgebra containing
Yeah,
the operators.
I'll write it in a second.
Thank you.
Okay, and I hope that today we will mostly be interested in the algebras A1 factored by, I want to say I for those these homogeneous ideals, but it will be a little bit wrong, so I'll be a little bit more accurate, and I'll write it in this ugly way. So we will basically we will be interested in algebra, in the quotients of the non-commutative disk algebra by some homogeneous ideals. Okay, so now I will begin with the interesting part. So let's also say that for these homogeneous ideals, its first and zeroth component for this homogeneous ideal, its first and the zeroth component are components are zero. So it doesn't have any x1 or anything at all, anything linear in it. That's not a big thing to ask of it. Okay, and then we'll give the definition I wanted to give from the start, the definition of a subproduct system. So this article I've read, it's a big article, and the authors of this article, they develop some really big and complicated science, about this, they formulate a lot of theorems about these subproduct systems. They want, and here we'll use it just a little bit. So a subproduct system associated with E is the following thing. It's a set of Hilbert spaces, xi of n, where xi of n is the intersection of the nth tensor degree of E and the set of P of E1, etc. En for P in the nth component of a homogeneous ideal. It's not the intersection, it's the intersection of this space and the orthogonal to this subspace of the full Fock space. And when I say we have P of E1, etc., En, it just means where, and P is a sum of some lambda E1 and EM. X E1, etc. XEM, or Z X. So I just say that that's the sum of lambda I1, etc. m, E1, etc. EM. So that's basically we basically look at these non-commutative polynomials as something as some vectors in the full Fock space.
Masha, I'm sorry to interrupt, just to clarify one point which is important in my view. So what is important is that your free algebra becomes a subspace both in the full Fock space in an initial way, but also in AN. So the correlation operators are independent in the sense if you take the generators of the free algebra to the operators as n, then this will be an embedding of the free algebra into AN. So the free algebra in some sense becomes a subspace both in the full Fock space and on the algebra AN, which acts on the full Fock space.
Yeah, that's right. Okay, so we've defined a subproduct system. It's quite a weird thing. No, we haven't defined it yet. And also, we take this set of spaces, this sequence of spaces, and for each space, there is a natural operator on P and E in the set of bounded space of bounded operators on E the 10th degree of n, which is just the orthogonal projection on the nth component of the subproduct system. Okay. So that's some weird thing, but there's just the beginning, and you'll see that it's important. Okay, now let's say that we have an ideal, as usual, and we also have now a constructed subproduct system. Now let's define a subspace of the full Fock space, which we'll call F with an index I, which which is defined quite naturally. It's just a Hilbert sum of the components of the subproduct system. And you also can, we also can look at this way. We can denote by I with a wave the set of P of E1, En for P in I. And this space, this Hilbert space, is just an orthogonal Ортогональное дополнение. Я забыла слово у нас было.
Orthogonal complement.
Complement. An orthogonal complement to this I with a wave. Okay. So now we have some Hilbert space. That's better than some weird subproduct system. And let's define the creation operators. So we'll define Si with an index I associated. Let's call it creation operator. Associated with I. which will act on Fi. Sorry. And which will do the following. For each x in the nth tensor degree, it will, no, I'm sorry, it's the wrong thing. So it is each y, it takes to ps plus 1 I of ei tensored by y, which when y is in the nth tensor degree. So basically, we say that we define this operator on the basis of Fi, and then we extend it on the whole Fi by continuity. Okay? Hope so. Great. Now that we have this marvelous operator. Now let's say that we will denote by AI n the Banach algebra generated by SIY, etc. SNI. And that's definitely a subalgebra on the algebra of all bounded operators on Fi. And the theorem which Shalit and Solel, I don't know how to pronounce it, proved is the following: that I is a universal n is a universal operator algebra. Do I have to I hope I think I have to remind what an operator algebra is. So I've defined this really nice and important algebra, which can be constructed by any homogeneous ideal with some small exceptions and condition, which some small conditions which we place on it. And now I'll go to the side. I'll remind what an operator algebra is, and then I will formulate the universal property of this algebra, and we'll see how marvelous it is. That's the plan. Okay, so definition. An operator algebra R is an operator algebra if R is just a subalgebra of the algebra of all bounded operators on some Hilbert space. The marvelous thing about Hilbert spaces is that we can take the direct sums and we can say that no, sorry. So when I have a Hilbert space, we can take a lot of copies of it. So if we have some operator in A. So we'll also can regard it as an operator in B of. No, I'm sorry. So if we have some Hilbert space, we can think of the space of bounded linear maps from the direct sum of n copies of this Hilbert space. And that's a simple exercise that's it is isomorphic as an algebra to the matrix algebra of n to n times n matrices, complex, of course, with the coefficients in the algebra of all spaces of V of H. Therefore, we have an embedding of the algebra of n times n matrices with complex coefficients, with coefficients in A. And yeah, I don't know why I wrote C here. I'm sorry. We have this embedding into the space of all m times n matrices with coefficients coefficients in the algebra of bounded operators of the whole Hilbert space, and we know that it's isomorphic to this algebra. So this thing is a Banach algebra. Therefore, we can induce a structure on this algebra and say that this is also a Banach algebra. We can induce a norm from this algebra to this sub-algebra. So when we have an operator algebra, for each matrix with the coefficients in this algebra, we can compute its norm. And there's a way of thinking about an operator algebra just as an algebra with a norm and a norm on all the matrices with coefficients in this algebra. But I won't get into it too deeply. Okay, so now let's define a completely bounded map. So suppose we have A and B operator algebras. We don't say that they have to act on the same Hilbert space. They're just some operator algebras. Each of it has some Hilbert space on which it can act. Suppose we have a map T from A to B. T is called completely bounded. If for any matrix with coefficients in A, sorry. The matrix, I'm sorry. I don't want to say completely bounded. I think. Sorry. I will say completely contractive. It will be better. So I will give a definition of a completely contractive map. So T is called completely contractive if for any matrix with coefficients in A, the norm of a matrix T of IEG, which is a matrix with coefficients in B. So the norm, we take the norm in this Banach algebra, is less than equal to the norm of the matrix we've taken initially. I'm sorry, just a second. My pen doesn't work for a bit. Sorry. So this norm is less than or equal than this norm. And so that's the definition of a completely contractive map. And we say that two operator algebras are completely isomorphic when we have two maps such that they inverse to each other, and such that both of them are completely contractive. The definition of a completely bounded map is pretty similar, just we need to say that we have some constant and put it this constant here, somewhere here. Let me check something. I'm really sorry. Can we wait a minute, and I will continue because.
Okay. Mm-hmm. We shall wait.
Yeah, I think now it's okay. So let's continue. And I will say that, so I will formulate the desired universal property of this Banach algebra, if you haven't forgotten about it.
Маш, демонстрацию экрана включите.
Does it work? That's so weird. Really?
О, супер.
Okay, now everything is all right. Okay, so I've defined the completely what was non-operator algebras, and the important fact about operator algebras is the following: that if we have an operator algebra A, and I is some ideal in it, closed ideal, then A quotient by I is also an operator algebra. It's a rather complicated theorem. I won't prove it. I'll just stated. Also, I will say, but I will explain what it means. So, which norm do we have on a quotient by I? So we want to think about these things, these spaces, and have some norm on them. So these algebras. But it's easy to say, to see that it is isomorphic to M and times N A quotient by M N times N of I as a vector space. So we have an isomorphism of vector spaces. And if we have a norm on this space, if we can say that this is a Banach space, it's a Banach algebra, but it's also a Banach space. Then we can say that this construction is a Banach space, and therefore we can induce the norm on this thing. So that's what it means, that a quotient by I is an operator algebra. And if we take just the matrices M of size 1, so just the elements of this algebra, then the norm on them is the same as a quotient norm. Okay, so I hope I've finished with the definitions and facts about operator algebras. Now we'll state the universal property of this algebra, this one. So it's definitely an operator algebra because it acts on some Hilbert space. Therefore, we can talk about some completely contractive homomorphisms. So the universal property goes like this. If we have n operators in n operators in the algebra of acting on some Hilbert space, such that for every p in our ideal, p of t1, etc., tn is 0, and also the norm of a matrix t1 tn 0 0 0 0 0 0 zeros. So there are a lot of zeros here, like n times n minus 1 zeros in the space of m n times n of b of h is less than 1, then we have then there exists a unique completely contractive contractive homomorphism phi from our algebra AIN to B of H, which takes the creation operators associated with our ideal to TI. And that is absolutely wonderful. Let's talk about why it is wonderful. Yeah, and it's unital, but I hope it's homomorphism. So in the article of, I think it was the 93rd, the year 1993, Popescu formulated a similar statement, but it's about an ideal. Basically that's it about an ideal that is equal to zero. The same statement about the zero ideal. So I probably should write it. So let's say it this way. If but he formulated it not about these algebras, but about sorry. So yeah, that's the same thing, but about the zero ideal. But I'll write it anyway. So if we take an, which is rather obviously equal to an 0, and if we take some operators in a Hilbert space such that this norm is less than 1, but we don't have any conditions on them because our ideal is 0, then there exists a completely contractive homomorphism. Phi from an to b of h that takes si to ti. So this is a particular case of this theorem, but this has been proven like 10 or 20, 10 I think, or 15 maybe years earlier. So we have from this particular case of this big theorem, we have a nice corollary. That I probably won't write it explicitly. That if we take A1 quotient by I, not by I will probably write it in this nice way I've written before, by the closure of this set, this ideal. Then this algebra I forgot the word.
Say it in Russian.
Удовлетворяет.
Satisfies.
Satisfies. Satisfies this universal property. And that's an easy exercise because if we have some operators that such that the ideal, our ideal, annihilates them, then by the Popescu theorem, we have a homomorphic, completely contractive homomorphism to B of H, and such that Si goes to Di. Here we have a quotient map. And we know that there is this, by the universal property of a quotient, there is a completely contractive homomorphism from this algebra to this algebra. Therefore, it's quite easy. But now we have two algebras, two operator algebras. This one and this one. And they satisfy the same universal property. Therefore, they are completely isometrically isomorphic. And that's an astonishing fact, which I really love. And now we have half an hour, so I can say something about the bundles of Banach algebras. I will forget about the fact that these algebras are operator algebras. That's nice, but I'm not sure if the bundles of operator algebras is a thing, or if it's something interesting. And I'll just say that if we have a complete isomorphism between these algebras, then these algebras are also isomorphic as Banach algebras. So we have a complete isometric, just an isometric isomorphism between them for any ideal homogeneous, and with some conditions. Great. So let's now. No, I will say something in a little bit. So why I love this fact so much? Because it says about a wide class of algebras that we can look at them from we can look at them from below and from the I'm really sorry. I should have learned my English better. And from the so we can look at it in two different ways. So it's a quotient of some algebra, and it's really useful. It's a quotient of some big universal algebra, and also it acts on some Hilbert space, and we know on which Hilbert space it acts. It acts on something really specific. Therefore, this is really useful. And one thing I also wanted to say is that I've defined our algebra AN of I as a subalgebra of operators on Fi. But I can say a little bit so sorry. So I can make so these are Fi is a subspace of the full Fock space. It's a Hilbert subspace of a Hilbert space. And if we have an operator on the subspace of Hilbert spaces, we can also think of these operators as an operators on the whole Hilbert space. Because if we have some T which takes Fi to Fi, and we have some element V in the full Fock space, we can define T of V as follows. So we take T of the orthogonal projection, the image of the orthogonal projection on Fi of V. So in some sense, our algebras, they act on the same Hilbert space. And that's what's amazing about it. Okay. So let me say something about the bundles of Banach algebras. This will be a long definition. So a Banach algebra, or a bundle of Banach algebra, a bundle of Banach algebras is the set of is a set of 4 elements. Some space E, which is just a set. Some topological set X, topological space X. A projection P, and gamma, which is also a set.
And finite or countable?
Hmm?
It is finite set or
no, it's just it's a really big set.
Arbitrary
set. Usually really big. So P is a map from E to X. So that's we can think about this as a total space. Just it just is a total space. And this is a projection. P is a projection, and of course we need to say so that's a bundle of Banach algebras. So of course we need to say that P sorry. So that P the inverse of any point in X is some Banach algebra. And that would be, so there are 2 questions. Why do we need the some space set G, the some set gamma, and what conditions do we need? Okay, so let's formulate these conditions. So I will name them as C1, C2, C3, C4, and C5 for no particular reason, just because I'm lazy, I suppose. No, I'm sorry. I also need to say that G is a subset of how do we write the space of functions from M to N. I'll try, and maybe I will be wrong. From X to E, so that's E to the power X. Right?
Okay.
Yeah. Okay. So the conditions. C1. So if we have some gamma in G, some gamma, small gamma in the big gamma, then the map X goes to the norm of gamma of X is continuous. C2. If we have some gamma and delta in gamma, in the big gamma, then gamma plus delta also belongs in gamma, where gamma plus delta of x is equal to gamma of x plus delta of x, because
I'm sorry to interrupt. Probably you forgot to say that gamma of x belongs to the fiber over x. That is to p inverse of x. This is essential because otherwise we cannot.
Isn't it what is already written?
Well, you wrote that gamma consists of some functions from x to e, but we have an additional requirement that little gamma of x sits in the fiber over the same point.
Yeah. I'm sorry. That's completely right. So yeah, I suppose. I thought that it's something somewhere follows from what I thought that it follows from what is already written. But just let's say that that's true. Isn't it?
Okay. So
Okay.
in other words, elements of gamma are sections of P. So the composition of gamma and P is the identity map of.
I understand. I have forgotten these things. So,
the notation is okay. This is just a term.
Yeah, we had to write the composition of P to gamma is this thing. Yeah.
Okay.
Right. Yeah. I'm right. Okay. Okay. So that's the second condition. And for some reason I wrote Banach algebras here, but it's no, it's okay. So that's also true for Banach spaces, but for Banach algebras we already need some additional conditions, I suppose. Okay, C3. If we have some lambda in C, then lambda and some gamma in beta big gamma, then lambda gamma is in beta big gamma, where lambda gamma of x is defined as gamma of x times lambda. Okay, C4. If we have, which is I think the most strong condition and the least natural one, if we have some function from x to e, and which is the section. So yeah, this is the condition that I forgot. P composed with gamma prime is equal to identical map on x, and also it's true for this gamma prime that for any x and for any positive epsilon there exists some gamma, small gamma in the big gamma, such that the norm of gamma prime of x prime minus gamma of x prime is less than epsilon for any gamma prime in x, then gamma prime is in G. Gamma prime is in the big gamma. And C5 is the most simple condition that for any x in x, the set gamma of x for gamma in the big gamma is dense in the inverse of x. Okay. And if we talk about algebras, I'm not sure if I have enough space here. I have to write an additional condition, but I'll try. So let's call it C6. That for any
I'm sorry, what is gamma prime?
Gamma prime is some function, some section of from x to e, and so basically I know what's the problem. I haven't said that this is a set of continuous sections. We can define what a continuous section is without defining what a bundle is. So we just define the set of continuous sections which apply, which satisfy these 5 axioms. And then we say that if there is such set and such total space and some topological space and such projection, then this whole construction, these 4 elements form a bundle of Banach algebras. So basically, you should think about these conditions as conditions on the continuous sections.
So the point is that we have no topology on E at this point, and we define continuous sections axiomatically. And the axiom C4 roughly means that if a section can be well approximated by a continuous section, then it is continuous itself. Is it correct?
Yeah.
Mm-hmm. Okay, thank you.
Yeah, it's completely correct. And so if we say about the bundle of Banach algebras, I'm sorry because I'm just now understanding some things that I should have understood later, earlier, much earlier. Then we need to say that the map of no, I'm sorry. Everything is all right. I'm just stupid and I panic. So the last axiom is completely normal. So if we have some gamma and delta in gamma, then we need to say that the map in each fiber, the map. No, I'm really sorry. I'm so confused. So I'm really sorry because I understand now that I just I have problems with the bundles of Banach algebras. I thought I understood it, but I'm just like really sorry. So I'll say that this is a bundle of Banach spaces, and that I will probably try to prove something or just formulate something for Banach spaces, and then probably after the talk I'll think about it more clearly.
Probably the only difference is that when you define Banach algebra bundles, you should also require that the pointwise product of 2 sections from big gamma is also.
Yeah, that's all. That's the only thing, because I'm looking on the definition and it seems like that's not what it's written, and I'm so confused. We just only need this thing, because I think I've proved it somewhere, but I'm not sure. So we definitely need this thing, and I hope that's all, because otherwise I'm utterly confused, and I'm really sorry. So, Alexey Yurievich, is that all?
Oh, yes, yes.
Okay, thank you. I'm sorry.
The only point that in condition 4, in your axiom C4, it seems to me that so you require this inequality for all x prime in big X. It seems to me
Yeah. I've
in the
written
real
something.
neighborhood of
I've written something really wrong, but I thought that it, but I thought the right thing. Yeah, thank you.
well.
No. I'm already wrong. So there exists some such delta.
There is a neighborhood of a little x such that for each.
Yeah. I forgot that that's not a metric space. Yeah, I have to move it around a bit.
I like your manipulations with.
Yeah, now I think it's complete. And now I think I don't have a lot of time, because I will formulate some statement, and I'm not sure that I will prove it, because the proof is just boring, and there are a lot of formulas that I can't read in English. Okay, so the statement I wanted to say the whole talk is like this. Suppose we have some metric space X. And suppose we, for all, yeah, we have a metric space, and we have a map from this metric space to the set of homogeneous ideals in the algebra of non-commutative polynomials graded. Ideal such that the first two components are zero, the zeroth and the first. Let's say that phi is continuous. I'm not. If for all, if for any operator tk, phi of tk phi from x, not operator, for any map, tk phi of x from x to b of e tensor k, e tensor k, such that Q maps to the orthogonal projection I'll write it this way. I'll write it like pi onto set P of E such that P of E1 En such that P in phi of Q n. So we define these maps, and we say that phi is continuous if all these maps are continuous. So I once wanted to formulate it in terms of Grassmannian, but I didn't manage. So I think that this is not so ugly. So, we just.
So what is the projection?
So it's a orthogonal projection on this set.
So what is the set?
This subspace. Yeah, I'm not sure how to say it better than it's written. If it's written correctly.
Okay, I see.
So we just basically we project on the nth component of the ideal. So basically, I want to say that all the components of the ideal, which can be regarded as some subspaces of some particular Hilbert space, finite dimensional. So they depend continuously on the point on the magic space. So that's all I want to say. And I just formulated in this maybe a little bit ugly way, but
that's okay. And when you say continuous, you mean that the space of operators is equipped with a strong operator topology. Is it correct?
I think that that's a finite dimensional.
It's finite. Okay,
so
it doesn't matter. I forgot it is finite dimensional.
Yeah, and that's maybe not too important. So maybe we can give some different definitions here, but in the work of Shalit and Solel, finite the fact that the spaces are finite dimensional are really important. Therefore, I'm talking only about finite dimensional space.
Okay.
So then we can construct a fibration of Banach algebras such that its fibers are the algebras we've talked in the beginning of the talk, the whole, so it goes like this. So if we have definition, suppose we have this phi from X to this ugly set. I'll just think I copied. And this phi is continuous. Let's define the algebras A, phi of Q, A phi of Q, which is just A n phi of Q. And as I've stated before, it can also be regarded as an quotient by the set of P of S1 Sn, such that P is in phi of Q, and we take a closure of this ideal. So now there exists a fibration over X with fibers which are equal. Which are equal to this. Well, let's state it. There exists not unique, just exists a fibration. Oh no, I just see fibration for some reason, but I need to say bundle. A bundle of Banach algebras E X P gamma such that P, the inverse of each point Q, is isomorphic to a phi of Q, where Q is for all Q in X. So that's the statement. I won't prove it definitely, but I have 2 minutes to define gamma, and I will end with it. Okay, so let's define gamma. So let's say that some small gamma is in the big gamma if for any x0 in X and for any epsilon which is greater than 0, and there exists a noncommutative polynomial in C of X such that and there exists some delta that is greater than 0 such that for all X in X, if X is so it's a metric space, so I definitely should write it this way: distance. If the X is close to X naught, then gamma of X is close to the polynomial, and this pi is just a projection onto our algebra from the noncommutative Dix algebra. So if we define gamma like this, then we can construct a fiber, and it's rather easy to check the axioms. And when we're checking the axioms, the most difficult axiom is the first one, because our definition is as weird as the fourth one. So the most difficult is the first one. And if we want to prove that it's semi-continuous, upper semi-continuous, then we use that it's a quotient of the big algebra. Explicitly, we use it a lot. And if we prove then, when we prove that it's lower semi-continuous, then we prove that then we use that it acts on one they all act on the same Hilbert space. And that's really useful that we can regard these algebras from 2 sides. Look at these algebras from 2 sides. I don't know if it's of any use, this construction, but I think it's nice because we can construct a wide class of bundles of the algebras associated with the noncommutative disk algebra. And that's pretty much it.
Okay, thank you very much. Are there any questions or comments?
Do you know something? Can we build a connection on total space?
I don't know. I know pretty much nothing about it. But when I hear connection, I don't like the word. So I hope not. But maybe we can. I don't know. It's an interesting question.
Also, that construction somehow reminds an attempt to build a shift category Banach algebras.
I didn't understand. Can you repeat it, please?
Vladislav, what was your question? По-моему, у Владислава что-то проблема со связью. Он не... Okay. Well, probably that was not a question, but just a comment.
Probably.
Yeah. Okay. Any more questions, please? Well, maybe I can just make a short comment on the subject, on this construction. So why are bundles of Banach algebras useful? There are many reasons why they are useful, but one of the reasons is that there is a general notion of strict deformation quantization, which was introduced by Mark Riffel. His definition of a strict deformation quantization involves bundles of sister algebras. Of course, here we have bundles of Banach algebras. So the fibers are not sister algebras, but are Banach algebras. But nevertheless, this construction is very close in spirit to Riffel's construction. And for example, if we consider something like a sister envelope of each fiber, it's very probable it can happen that we can get a sister algebra bundle on this way. And this can give us some way of constructing strict deformation quantizations in the sense of Riffel. And there are other reasons to consider such objects, because they are closely related to some results in non-commutative complex analysis. Okay, if there are no more questions, then we thank the speaker. Thank you, Masha. And next week, our speaker will be Vladislav Pakitkin.
On which topic?
I don't remember exactly, but I hope to see you next week.
Thank you.
Okay, thanks everybody.
Thank you.